is really just a variant on the idea of induction, but it's something that comes up often. And my plan is on Friday to talk more about we'll probably do a bunch more like writing stuff in Disco and talk about what induction has to do with programming, because it turns out that the answer is quite a lot. So, so remember that normal induction, which we talked about last time, right? If you have some proposition you're trying to prove for all natural numbers, basically if you can set up this chain like this, you say, all right, I prove it for P0, and then I prove that each thing would imply the next, then I've proven it for all natural numbers. But what if, what if these, what if each thing doesn't always imply the next? So in particular, what if we have, so let's say that P0 did imply P1, but let's say, I don't know, maybe and maybe P1 implies P2, but maybe P3, maybe P1 implies P3. Oops. P1 implies P3, but P2 doesn't imply P3. And maybe P4, maybe P2 implies P4, but not P3. And maybe P5, maybe P1, oops. Maybe P1 and P3 together kind of imply P5, or something like this, right? So, I haven't shown you what's in the ... right? But so far, just what we can see here, is this still okay? Are all of those true? It's assuming that P0 is true. Are all of these true? Yes, right? Because, well, P0 implies P1. That implies P2. P3 is true because P1 is true, right? So then, and then P4 is true because P2 is true. P5 is true because these are both true, right? So actually, requiring that, each thing has to specifically imply the next one, that's maybe too strong, right? So we could get away with something weaker as long as each thing is implied by something that came before it, or possibly multiple somethings that came before it, right? Then they're all going to be true, because each one, I'm going to say, well, I already know all the ones before it. Sorry, this way. I already know all the ones before it, and so they're all true. Therefore, this one is true by some combination of them, and then, say sometimes, just to summarize what I just said, sometimes requiring each pk to imply pk plus 1 is too strong. It's an unnecessarily strong requirement. Right, it should be fine as long as what? As long as each pk plus 1 is implied by some previous, we'll just say pj, or pj's. So to do this, we're gonna define something called the principle of strong induction. So strong induction says something like this. Right, if we can prove P0 and for all natural numbers k, now with normal induction, weak induction, we just said if pk implies pk plus 1. But now we're going to say, look, if all of these things together, P0 and P1 and P2 and ... and pk, if all of those together imply pk plus 1. Right, then for all n, pn. Right, so the only difference with so-called weak induction that we talked about on Monday, all we assumed here was that pk is true, and then we had to show that pk plus 1 is true. And sometimes that works. And here we're saying, no, you know what, it should be okay to say, look, you can assume that all the previous ones are true, and if you can somehow use the assumption that all the previous ones are true to show that the next one is true, that works also. Now, we don't have to use all of them. This is just saying you get to assume they're all true, and then you have to show pk plus 1, but maybe you only need, you know, if these are all true, then in particular, like, you know, p1 and p3 are true, so maybe I just need those. So that's fine, I can just ignore the rest and use those. But the point is I get to use kind of whichever previous ones I want. Okay. You know, the dot 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 is not super formal. We could write it more formally by saying, you know, by putting some kind of for all here, saying, you know, for all j less than or equal to k, p of j or something like that. So I'll just write it here, so like more formally. We would say something like, if p0 is true and for all k, for all j less than or equal to k, so that implies p plus 1. I'm just writing that down here just kind of for completeness, but like it can be a little confusing thinking about like these nested for alls and whatever, but really it's you can think of it like this. So there's actually a few ways even that we can even make this more general. I'm just going to talk through them though. I'm not going to write it out formally because at some point writing out all the notation for it just kind of becomes, it starts to become less helpful, I think. So one thing is, well, we don't always have to start at 0. Just like we saw an example on Monday where we actually wanted to start at 4, not at 0, because it wasn't true for the first few numbers. The same thing can happen here, right? And all you do is you just say, all right, well, instead of having our base case be 0, we'll start at whatever we need to start at. So, you know, p of 5, and, you know, if it's always true that, you know, p5, p6, p7, you know, all the way up to k, then we can show through. The other slightly trickier thing, and we'll do an example where we'll see this happening. We'll do probably maybe a couple of them. Sometimes one base case is not enough. And the reason for that is sometimes, like maybe to show each pk plus 1, you always need to know like the 2 previous things or several previous things. And the very first one wouldn't have, like p1 doesn't have 2 previous things, it only has 1 previous thing. So maybe you need to prove p0 and p1 separately. And then starting from p2, you can say, well, for each of those things, I'll have like the 2 previous things that I can use. So say we can also start at base case other than 0. And I'll just say sometimes we need more than one base case. I'll just say C examples. I think when we do an example of this, it'll become much clearer. And it's one of those things where like it's always fine to just try with a single base case, and then at some point, if you're being careful, you'll realize that you're stuck and that you need another base case. You can go back and ask. Garrett.
Maybe on an example of that for like a weak reduction, would it be like the Fibonacci numbers?
Yeah, that's the example we're going to do. Yeah, exactly. That's exactly. We're going to do an example with proving something by the Fibonacci. Yep. No, that's good. Okay. So one thing I will mention, it seems like, I mean, it's called strong induction, so it seems like it's stronger than the other kind of induction. Strangely, they're actually completely equivalent in the sense that you could actually prove that strong induction works using only weak induction. It's a little mind-bending thinking about how you would do that. I'm not going to go through it, but if you're interested, you can ask me, or I can point you somewhere. Clearly, this, if you have this principle, then you could turn that into weak induction, because like, I don't have to use all these. I can just ignore all of them except pk, and then I'm back to doing normal induction. It's less obvious that you can go the other direction. It turns out that you can. So really, there's just induction. Strong versus weak, it doesn't actually make a logical difference. However, when you're communicating with humans, it can be helpful to like signal what kind of argument to expect. So you say, oh, this is a proof by strong induction or a proof by weak induction. Even though, kind of from a logical point of view, it doesn't overlap. And it's certainly not obvious that weak induction implies strong induction, so that's why we talk about it as a separate thing, because it's helpful to have it kind of as a separate concept in your head. Okay. So let's do some examples. The first example I want to do is the fundamental theorem of arithmetic. And we've seen this before, but we didn't prove it, and I said, well, we can't prove this yet because we need induction. So we're not actually going to prove the entire thing, we're going to prove part of it. But if you recall, the theorem basically says every positive integer can be written as a product of primes. And also, uniquely, like, and this is the part, I'm putting this in parentheses because we're not going to prove this part today. So it is true that, you know, any integer, there's only one way to factor it into primes. Of course, you can put them in a different order, but we don't care about that. If you don't care about the order, there's only one way to do it. We're not going to prove that part. That part, it's actually not that hard to prove, and again, if you're interested, I can point you to where you can read about that proof. But we're going to focus on just proving the fact that it is possible to always take any integer and turn it into, you know, a product of a bunch of prime numbers. Which, you know, maybe you think that doesn't really need to be proved. It kind of seems obvious, but I think it just seems obvious to you because you've done it a bunch. So you're like, yeah, of course you can do that, because I do it all the time, but it's not obvious. And there's some systems of number-like things where this is not true. Right? You can't always factor things. So, proof. So let Pn be the proposition n can be written as a product of primes. And so we want to prove for all n greater than or equal to 1, so first, we'll just say if n equals 1, I'm just going to kind of get rid of this case because if n equals 1, I'll just say n equals 1 is a product of no primes. So we're just going to focus on n greater than or equal to 2. So it's true for n equals 1. That's not really my base case. I'm just saying, that's a separate case, and that's true, so we're just going to not worry about that one now. Now we'll just focus on proving that it's true for n greater than or equal to 2. So what I want to do is, let's try a proof by weak induction, and we're going to see what goes wrong. And that's going to help us understand why sometimes we need strong induction. And then we'll fix it, and we'll use a proof by strong induction. So let me go on the next page here. I'll just actually, let me say, we'll focus on proving for all n greater than or equal to 2. So, attempt, so here's our attempt number 1 with weak induction. And I'm just going to put this here. Remind us. This is going to be a failure, right? So don't look at this in your notes and be like, oh, this is a good example for me to follow. Right? Not a good example. You know, sometimes I actually wonder if maybe I would do you more of a service by spending just as much time like writing down wrong proofs and then talking about why they're wrong than just always doing correct proofs. Because, of course, you know, when you're doing stuff, you probably spend half your time writing down wrong proofs. That's what you actually do. So, anyway, we'll do it in this case. So, well, we need a base case. So when n equals 2, it is already prime. So it is in fact a product of primes, it's just 2. So check. Okay, now for our induction step, we're going to say, you know, let k be greater than or equal to 2. I mean, it says arbitrary integer. Really, I mean an arbitrary integer greater than or equal to 2. So, and we're going to suppose p of k. That is, what does that mean? P, or proposition P means something can be written as a product of primes. So we're going to suppose that k can be written as a product of primes. And then we have to show pk plus 1. Right, so we must show pk plus 1. That is k plus 1 can be written as a product of primes. Okay. Well, I want to say there's two cases to consider. So k plus 1, it might already be a prime, or it's not. Right? One of those is true. So there are two cases. So first of all, if k plus 1 is prime, then check. It's already a prime, so sure, it's a product of just that one prime. Otherwise, we can say that k plus 1 is not prime, so it has some factors. So we can, like the definition of being prime says it's only divisible by itself and 1. So if it's not prime, there must be some other divisor that it has. So we can say, I mean, we can't just say, oh, you can factor it into primes. That's what we're trying to prove. But by definition, we can say that we can factor it somehow into like some A times B, where A and B they're not 1 and they're not K plus 1. Right? They're something other than, so they're in between 2 and K. Okay? This is where I get stuck. I would really like to say that I can write A and B as a product of primes. So therefore, when I do A times B, like it's a bunch of primes times a bunch of primes, and I get a bunch of primes. However, I don't know that. My induction hypothesis only tells me that K can be written as a product of primes. But I mean, A and B, one of A and B might be K, but it might not be. Actually, it can't possibly be K. Because we'd have to multiply, it'd have to be like at least half, or like at most half of K. Because we're going to multiply by 2 to get K plus 1, or something. Whatever, the point is, my induction hypothesis doesn't actually tell me anything about A and B, and so I'm kind of stuck. So we're stuck. We don't know anything about A and B. Right, we only know okay, but strong induction comes to the rescue here, right? Because strong induction says, oh no, you don't only get to suppose that this is true for this one value k. You get to assume it's true for anything less than that. So, k, you can assume that k can be written as a product of primes, also k minus 1, k minus 2, all of those numbers all the way down to 2. You get to assume they all can be written as a product of primes. And so that is going to include A and B. So I'm not going to, let's see. So attempt number 2. So the base case, this is using strong induction. The base case is the same. And the induction step, we're going to let k greater than or equal to as before. And suppose, here's where it's different, right? I'm not just going to suppose that pk is true. We're going to suppose that I'll say pj is true for every j, or I'll say every, from 2 up to k. Right? In other words, any number less than or equal to k can be written as a product of primes. And then I'll just say, as before, if k plus 1 equals ab, right now we know that a and b can be written as products of primes. Hence, so can k plus 1. So Garrett mentioned the Fibonacci numbers. So if you don't know what those are, so they're defined this way. So F0 is 0, F1 is 1, and Fk is equal to the sum of the two previous numbers. So Fk minus 1 plus Fk minus 2 for k greater than or equal to 2. So in other words, we start with 0, 1, and then at each step we add the two previous numbers to get the next number. Right, so we'll get 0, 1, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 5, 8, 13, 21, 34, 55. So these are pretty famous, and if you've never seen these before, go look up a Wikipedia page about them or something, and just pick a random part of it and read it. I mean, they're famous partly because people have defined these since hundreds of years ago. Also, they just show up in lots and lots and lots of places, and they have lots of interesting properties. So we're going to try to prove some things about them, and we'll see kind of what we end up needing in order to do that. So one question we might have, if we try some examples, you can see that it may be not so obvious quite yet, but if you keep going a little ways, you see that they get big really fast. Even I think like, do I have? Oh yeah, I have here my notes. Like if we keep going 100, so the 100th Fibonacci number has like, how many digits is that? It's like 24 digits or something like that. So I don't know what that is, like a squillion, 3 squillion. No, I don't know, they just get big really fast. So one question we might have is, well, how big do they get, right? So we proved a theorem the other day about factorial, that it was actually bigger than, it was growing faster than 2 to the n. So we can try to prove something similar about Fibonacci numbers. It turns out Fibonacci numbers are less than 2 to the n, although they're kind of similar in how fast they grow. But we're going to, we want to prove that for all natural numbers n, Fn is less than or equal to 2 to the n minus 1. And we can try some examples just to see if we believe this, right? So like, here's, let's make a little table. Like, here's my n, here's Fn, here's 2 to the n minus 1. So, 0, 1, 2, 5. Fn, we can just read them off of our list up here. So 0, 1, 1, 2, 3, 5. And 2 to the n minus 1, let's see. When n is 0, 2 to the minus 1 is a half. 2 to the 0 is 1. 2 would be 2 squared. Or no, 2 to the 1, which is 2. And then, okay, we're just going to keep. And so you can see that this column is always less than or equal to this column, right? The 1 is actually equal, but that's the only place where it's actually equal. Everywhere else it seems like it's strictly less. And you can keep going, and it definitely looks like that continues. So, how can we prove this? So let's, we're going to do the same thing. So again, we're going to try weak induction, and we're going to see what goes wrong, and then we'll fix it. to let k be a natural number, and suppose fk is less than or equal to 2 to the k minus 1, then we need to show, we must show, well, this is like our proposition for k. We need to show the proposition for k plus 1. So that would be saying that fk plus 1 is less than or equal to 2, well, it's going to be k plus 1 minus 1, which is just k. Okay. Well, to show that something is less than something else, or less than or equal to, right, a good bet would be to use a similar technique that we've done a bunch before, where we just start with the first thing, start with fk plus 1, and see if we can do some, some steps until we get it to 2 to the k. So we're going to say, all right, fk plus 1. Well, what can I do with fk plus 1? Well, I have my definition of Fibonacci numbers, right? So I could say this is equal to fk plus fk minus 1. Right, so this is by definition of Fibonacci numbers. And then, well, I know something about fk, right? I suppose that fk is less than or equal to 2 to the k plus 1. So I could replace that, and I could say, well, this is less than or equal to 2 to the k minus 1 plus fk minus 1. This is our induction hypothesis. And now I'm stuck, because I don't know anything about fk minus 1. So I'm stuck. I don't know anything about fk minus 1, right? Our induction hypothesis only says something about fk. And so I think this is what Garrett was alluding to earlier. Because the Fibonacci numbers are defined, right, each one is defined in terms of the 2 previous Fibonacci numbers. If we're trying to prove that Fibonacci numbers have some property, then probably to prove that, a certain Fibonacci number has the property, we're going to need to know that property about the 2 previous ones, because it's defined in terms of both of them. Right? So just weak induction, where we only assume something about the 1 previous thing, is not going to be enough. Right? We need to know something about the 2 previous things. There's actually one other thing about this that is wrong. So something about, so not only are we stuck, there's actually something that I wrote here that's not correct. I did it on purpose. And it's a little subtle if you're not thinking about this. So I said here that according to the definition of Fibonacci numbers, fk plus 1 is equal to fk plus fk minus 1, right? However, that's not true for any k. So if we go back to the definition says, well, as long as k is greater than or equal to 2, that's true. Right? But what do we know about k here? All we know is that it's a natural number, right? It could be 0. And in that case, fk plus 1 would actually be f1. And this would be saying that f1 is equal to f0 plus f minus 1. It doesn't actually make any sense. So what's happening here is something that I alluded to earlier, where I said sometimes we need more than one base case. Because if we only have one base case, f0, then I try to prove something about f1. But like I can't prove something about f1 if I only know something about the 1 previous number, right? So I actually am going to need to prove it for f0 and f1, or just show those cases separately. And then when I start with f2, I can say, well, that's true because it's true for f0 and f1. And then f3 is true because it's true for f2 and f1. So this step is invalid. Right? It's only true or I'll say it's the definition doesn't apply Any questions about that before I fix it? Alright, so let's improve section number 2. This one will actually work by strong induction. So, base cases, well, F0, we already did F0, right? So F0 equals 0, which is less than or equal to 1/2 is 2 to the 0 minus 1. Check. And let's check the case for 1. So F1 is 1, and 2 to the 1 minus 1 is also 1, so they're actually equal. Check. And for our induction step, we're going to, so let k greater than or equal to 1, right? So, and we're going to suppose fj is less than or equal to 2 to the j minus 1 for all j less than or equal to k. Okay, so everything from 0 on up, and really I only need the 2 previous ones. So in some sense it's overkill to say, suppose it's true for everything less than it, but whatever. I mean, we don't have to use all of those, so it doesn't matter. And also, it's important that I said, because I already did base cases 0 and 1, I can say, all right, now we're just going to start at 1, or anything from 1 on up. That's what we're going to be able to do our induction step. So, and we must show fk plus 1 is less than or equal to 2 to the k. Okay, and we're going to do a similar thing that we did before, but it's going to work this time. So fk plus 1 is equal to fk plus fk minus 1. And this is, by definition, of the Fibonacci numbers. Right? But unlike the previous time, we're actually allowed to do this because we know that k is at least 1. And that means that, fk plus 1 is at least f2. Because that definition does apply. Right? Note k is greater than or equal to 1. So this is allowed. Well, now, my induction hypothesis tells me that I know something not only about fk, but also about fk minus 1. Right? Anything k or smaller, we're assuming that this is true for them. So I can, if I replace each of them with, so I know that fk is less than or equal to 2 to the k minus 1, and I also know that fk minus 1 is less than or equal to 2 to the k minus 2. This is my induction hypothesis twice. I guess you could do it one step at a time if you wanted, but I just replaced them both. Since each one I'm replacing it by something bigger, the whole thing can only get bigger, or stay the same. Okay, well, one thing I can do at this point is I can say, all right, I have 2 to the k minus 1. I also have 2 to the k minus 2. So if I replace this 2 to the k minus 2 with 2 to the k minus 1, that's going to make it bigger. It's multiplying by 2. right? Because, you know, maybe this would be something like 2 to the 5th, but then 2 to the k minus 1 would be like 2 to the 6th, so it would be getting bigger. So I could replace it. Well, I can actually say it's not less than or equal to. It's definitely not equal to, right? It's just less than. So this is the fact that 2 to the k minus 2 is less than 2 to the k minus 1. Okay? Well, now that's equal to 2 times 2 to the k minus 1, which of course is equal to 2 to the k. This is just algebra. And that's what I was trying to show, right? We're trying to show that sk plus 1 is less than or equal to 2 to the k. So questions? And I have a challenge for you. I'll probably put this on the next module as like a level 2 question, but just while we're thinking about it. So this, just stepping back and thinking about, you know, Fibonacci numbers. This one says, all right, Fibonacci numbers don't grow quite as fast as 2 to the n minus 1. But we can prove something else to show that for all n 3 halves to the n is less than or equal to, well, I'll say prove for suitable values of n. And what I mean is, it might not be true literally for all natural numbers, but kind of similar to the thing we did on Monday where it was only true from 4 on up. The goal is to find some n such that, you know, maybe like 3. You know, well, when n is 3, this is true, and then for everything after that, it's always true. The point is, this is showing that, you know, the Fibonacci numbers are somewhere in between, you know, 1.5 to the n and 2 to the n. So that gives us a pretty good idea of how fast they grow. You can actually prove something much more specific than that, but this is a nice thing we can prove without actually needing a lot of fancier math, just kind of using some basic algebra and induction.